quick recap for the recording. Today, we're going to talk even more final exam problems. The first one is a derivative problem. We have a function of three variables, and we're considering a particular level surface of this function of three variables. And I asked the standard first derivative calculus questions. Find the equation of the plane tangent to the surface at a point. Which direction has the biggest partial derivative at that point? And then a question about directional derivatives. You can tell it's a directional derivative question because I've given you direction. I didn't give you a unit vector though, so fair warning. Problem 7. We have a function of two variables, and I want you to find the critical points. And you can guess what I'm going to put for part B. Classify each critical point. As a local minimum, a local maximum, or a saddle point. Another classic derivative problem. Find and classify the critical points. Here's another problem that grows out of a single variable calculus problem. Let's consider a plane in R3, and let's consider a point that is not on the plane. Find the point on the plane that is closest to not. I'll include the suggestion to use Lagrange multiplier. Find the point on the plane that is closest to naught. This is just an expansion of a problem that you can do in Calc 1 or even in geometry. You have a line. You have a point not on the line. And we want to find the point on the line that is closest to naught. And so we know geometrically what we need to do. We need to go draw a line perpendicular. We need to go from P naught perpendicular to the line. That's going to be the shortest distance. And our job is to find this point. The change that we've made here, since now we're super skilled multivariable calculus and all sophisticated, we just trade our line for a plane. I'm just looking at it from the side where the plane looks like a line. Any questions? I am going to give a hint. I'm going to give you this hint to make your calculations simpler. Don't minimize the distance. Minimize the square of the distance and then just take the square root afterwards. Minimize the square of the distance. Remember, the distance formula has the square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared. So minimize the square of the distance. Then you won't have to use the chain rule in your derivatives. That's probably too much hint. I should have let you suffer, but I'll cut that part of the video. So but then you'll just tell everybody else to minimize this. He said to minimize the square of the distance, and I freaking just wrote it. So I'd have to erase that, edit the video to create another reality. Question. So the theme for today is clearly Calc 1, but in Calc 3. Yesterday we were about integrals. First day we were about vector calculus. Today we're about derivatives, which comes from Calc 1, but in a Calc 3 style. Any questions? Like I said before, these are the problems that are going to show up on Canvas. You can start working on these problems. I'm just going to ask you to upload an image of your work. So you can either write it on paper, take a picture and upload that, or you can write it on a tablet and just upload images from there. Or you'll have to type text box available if you want to type everything out. Because you like suffering and trying to type things on computers and make it come out correctly, then by all means, you can use the limited capabilities of the equation editor. Any questions? Comments? All right, that's our set of problems for today. Partial derivative questions, and then on Monday we'll have one more round of questions that'll be mostly about describing stuff that I forgot. I'm going to check through my extra set of final exam style problems, and we'll talk about those on Monday. Any questions? Comments? Snide remarks? All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.